Hey crew, and welcome to our calculus boot camp. This is going to be one of your first of many lessons that I record and then post for you. My goal is to post a lot of these that you watch in your own time. That way when we come into class, our live sessions, we can actually go over examples that apply what was talked about in the mini lesson. The purpose of calculus boot camp in general is to make sure that every student is coming in with the same level of calculus knowledge that we need. If you've already taken calculus, this should be a review, but hopefully a good review, and also to give you an idea of what type of calculus we'll be using. And if you have not taken calculus, this is going to give you the bare bones of what you need in order to jump into our first unit. I will say, big note, if you have not taken calculus, you are taking it this year, please make sure that when you learn this in your class, you do it the way your teacher tells you. So when you learn what I'm going to be telling you in calculus, you're going to go the long way. You're going to learn a lot of the definitions, the theory. That's extremely important that you understand that, and you do it the long way first. So don't jump in with these shortcuts that I'm teaching you in your math class. These are physics only shortcuts for the minute. So the first big term that we need to know is going to be derivative. That should be a D. Oftentimes, when we're talking about a derivative, we're going to see it represented by two symbols like this, dy, dx. D of some variable over d of some other variable. D is actually originally started from the big lowercase delta, and then we also have our uppercase delta. They're all related to each other, and we know that when we're in science and math, delta represents change. So it's as one variable changes compared to the other. So the bigger definition that we are going to use here is rate of change of a function. Now, if you've actually taken calculus, you know that the definition of a derivative is much bigger than that. But for our sakes, that's where we are going to start, because that's where we're going to find the most amount of value for us. So we need to look at some different types of functions in order to take this definition a little bit further. We're going to start with the linear. So one of the first things we can see is that this function is increasing from negative infinity to infinity. Okay, the entire time we're looking at this function, it is increasing. So that gives us a hint from the beginning that maybe this has something in common with the rate of change. Well, one of the things that we know about the definition of a linear is that there is a constant rate of change. That constant rate of change is known as slope. Constant just means that no matter where I am, my slope is the same. Notice if we come back over here, dy dx, if we think about it as that delta, all of a sudden it's delta y over delta x, which we know to represent slope. So therefore, derivative and slope are highly, once again, highly related. What makes a linear really cool, let me come back over here to my linear, is that there's this constant rate of change. So no matter where you are, it's going to be the same. If we say that this is y equals 2x plus 3, that seems to be a probable equation for this function. We know that the slope is 2. That means when I'm here, my average rate of change is 2. When I'm here, my rate of change is 2. When I'm here, my rate of change is 2. No matter where I am on this function, my rate of change is 2. So for this one, if y equals 2x plus 3, then dy dx equals 2. Pretty cool. Linears are the easy one though. Let's come over here and talk about quadratics. That was a really great quadratic that I drew, I know. So let's just say, I'm going to make up a totally weird equation for this. It's probably not right. But this is x squared minus 8. We're just going to say that that is the function that we're looking at right now. If we start back at the increasing and decreasing, we're going to make that my vertex. It looks like this one is actually decreasing from negative infinity to 0 and increasing from 0 to infinity. Because there's two different intervals here, we have a decreasing and an increasing. We know that the rate of change is different in different parts. The rate of change right here, actually, I could draw this line here, and it looks to be 0, versus the rate of change here is a negative rate of change, and the rate of change here is a positive rate of change. I just made that very messy, so I'm going to erase some of these things that I'm talking about. Let's go back to get my x-axis back on here. All right, ignore all of those oopsies. Still trying to get used to my new device, so sorry for that. So derivative, once again, is saying those different rates of change. I pointed out, and I'm going to change my colors here, that we could have taken the rate of change here, and it looks like this. The rate of change at this point would be 0. But say that we try to draw a line over here. It looks like the rate of change there might be a really big positive number. And if we try over here, oops, let me change my color again. We can see that this one is negative, but maybe not as high as that one. So all across this function, we have different rates of change. Each and every one of these represents the rate of change at a specific point. So if we come back to this definition, when we're talking about derivatives and we're talking about the rate of change, that's an at symbol, at a point. So there's two different things that we can do. We can either come up with the equation of what the rate of change would be. We can plug in any x value and find where that rate of change is. That's where we see the dy dx. Or we can talk about the derivative of a point. We can talk about the rate of change at that specific point. So we had 3 different specific points pointed out here. So to kind of pull all of that together, there's 2 different ways that we can look at derivatives. There's the graphical definition, which is the slope at any or all given points of a function. When we say the slope here, we're actually talking about the slope of the tangent line. Now, maybe you've heard of a tangent line before, maybe you haven't. So we're gonna rewind just a second and talk about circles. What? Crazy, right? But I know that all of you have studied circles at some point, and you learned that a tangent is a line that intersects the circle once, aka touches. Well, that's actually just pretty much the definition of a tangent line in general. It doesn't have to be circle specific. It just means a line that intersects only once. So we can even come back up here to the example I was looking at earlier. My colorful lines here are all tangent lines. They all intersect my function at exactly one point. And notice I was trying to estimate the slope of those points. So when we're finding the slope of the given function, we're talking about the slope of the tangent line at that exact point. From those, we can often sketch graphs. We're going to talk about that more when we do our motion graphs, what I call our motion graphs. So really our kinematic we're going to talk about x versus t, v versus t, and a versus t graphs next week. When we talk about these, we'll talk about taking a function here and from it being able to create your other functions or going in the other way. So it's really important that we understand how motion all relates together, and this is going to get us here. So while I have this pulled up, this is actually a great time to talk about how they're related. Going in this direction, you use derivatives. So the slope of this would become here. And I can even do that really quickly. We can see that it's negative and it starts really high. It's negative and it starts really high and gets closer and closer, like negative, I don't know, 10, and then gets closer and closer to 0. So we could start it here, and we're going to say it's negative, but it's getting closer and closer to 0. At this point, we said it was 0, and then up here, we're going to see that same pattern. So I was able to create my velocity versus time. Well, this is a linear, so all we have to do is determine what is the rate of change of this. I know that it's a positive number because it's going up, and we know it's the same one everywhere. So we're just going to have a straight line here. Once again, I know I went through that really quickly. We're going to talk about this more next week, but just so you can see them together. If we're going in this direction, derivatives, we're going to go in this direction, something that is called an integral. For today's sake, we're just going to consider integrals, antiderivatives. They are just the opposite of a derivative. They undo the work that we did of a derivative. But if a derivative is slope, then an integral is the area under the curve. When we say the curve in upper level math, we just mean the function itself. It doesn't actually have to be curvy. So this one looks really easy. If we're saying from 0 to some t, we can actually draw a line. We're talking about that area here. We're talking about the area here and the area here. So when we're saying under the curve, we're saying between the function and the x-axis. This one would be kind of hard because it would be kind of all of that. It looks a little creepy. So that's what we're talking about when we're talking about the area under the curve, is the area between the function and the line itself. So those are some of the really important graphical definitions. What we're going to look at is how to take a derivative algebraically. Now, I'm going to show you the easiest version. It is one way. It's only going to work for a handful of functions, but honestly, the majority of the functions that we deal with, this is all you're going to need to know. You're going to learn other things, the chain rule, the product rule, the quotient rule. Don't get me started on all of them. You're going to learn your trig ones. Those ones can be more difficult, and on occasion, we will need to use some of those. But most of the time, we're only going to need to use what is known as the power rule. You can use the power rule to take the derivative of any polynomial. So that's what we're going to be dealing with most of the time when we're taking derivatives, is a polynomial. So what I mean by that is, say that we had 3x squared plus 5x minus 10. We all know that that is a polynomial. So I'm actually going to represent this as I do it with the rule as a of x to the n plus b of x to the m plus c of x to the z equals y. So in order to take my derivative, dy dx, we're going to follow, like I said, what's known as the power rule. In the power rule, the first thing you do is you multiply your coefficient by your exponent. So I'm going to have n times a. I'm going to keep my x. And then my exponent is going to become n minus 1. We're going to do that for every single term. So I'm going to end up with m times b to the x to the m minus 1 plus, I'm going to have to come down here, z times c to the z minus 1. Looks like really scary math notation. Honestly, if you're in APC, you really should feel comfortable with me doing this type of notation. If not, that's okay. We're going to try and get there, but we're going to do a ton of things in variable form as we go along. So try to do your best to keep along with the variable notation. But let's go back to the example I was talking about. I had 3x squared plus 5x minus 10 equals y. I'm going to be honest, I think that's what I had written down. We're going to go with it. So the very first thing I'm going to do is I'm going to bring the 2 down. So it's going to be 2 times 3 to the x of the 2 minus 1 plus, well, if we think about it, that's not a 0. That's an empty hole. Let me make that a question mark. We have to figure out what exponent's actually there. We know that any exponent without, or any variable without an exponent shown actually has a 1. So 1s as coefficients, as exponents, we don't need them, so they'll go away. So what I'm going to do, that's going to be 1 times 5 times x to the 1 minus 1. And then we're going to deal with this last term. This one's really interesting. So it's going to be negative. Well, there's not an exponent here. So if there's not a variable here. So if there's not a variable, there's really an x to the 0. So I'm going to bring that 0 down. So it's going to be 0 times 10 to the x to the 0 minus 1. Now we can actually fill all these out. So 2 times 3 is 6. 2 minus 1 is 1. Well, I know I don't actually need that anymore. 1 times 5 is 5. X to the 1 is 0. I know that I don't actually need x to the 0. Minus, well, 0 times anything is 0. Okay, well, I know I don't actually need that either. So this is my function. That means, say that, okay, I'm just going to do a quick graph here. This is a positive quadratic. This is going to open up. There is a y-intercept at negative 10. We're going to say that it looks like this. That was just my very quick, I could be completely wrong. I just took those two characteristics. What I'm saying is that I now have the function for the slope at any point. I can actually find the vertex pretty easily, or the x of it, because that's where this would be equal to 0. Anytime we have a turning point, your derivative is going to be equal to 0. So once again, a turning point, aka max or min, has a slope equal to 0. So this is saying I could put in any one and find what the slope is at that point. So if I put in 0, we'd have 6 times 0 plus 5 equals 5. So it's saying that at this point, if I were to draw a tangent line, the slope of that line would be equal to 5. You know what? That actually looks like it could be pretty close. My sketch may not be that far off. So that is when we're finding the equation, that's what we're actually doing. So we're finding the slope at that point. We're saying what is the rate of change at that very specific point, or it gives us the function to be able to find that. So let's do another practice with the power rule. And then you come up with an equation. I'll give you a second, see if you can do this on your own really quickly. All right, let's see what you came up with. So I'm going to bring that here. That's going to give me 50x, and then 5 minus 1 is 4. And then 4 times negative 6 is negative 24, x to the third, plus 6x squared. I hope you noticed earlier that when you have a constant, aka there is not a variable, you're going to end up multiplying by 0, so that term just disappears. And that is the easiest way to take a derivative. We've done it. Woo! Talking to my computer seems a little weird, so indulge me as I make silly jokes, because I would definitely make silly jokes in class. So So that's our basics for a derivative. You're going to see it, it's really easy. And remember that we're talking about the slope, the rate of change. I do want to quickly talk about what it might look like to take the antiderivative or the integral. So let's go back to the example we had earlier. I think I was using purple. We said that dy dx equals 6x plus 5. Well, I want to know what y equaled. So we took the power rule to get here. So we're going to want to undo the power rule. Actually, I know you're not actually sitting here with me, but I'm going to give you about 30 seconds because I'm going to get bored. See if you can figure out how to go backwards. You have the correct answer earlier, but see if you can figure out the pattern on how to go backwards from this to the original function. As you do that, I'm going to write some new things. Okay, while you were thinking about that, I just want to get some of this right here. So this is how I'd actually set this up. This symbol is for an integral. That's what I have down here. So I'd say the integral of 6x plus 5 dx is equal to y. So it's going to undo this. It's going to let me go back to what the original function was. This symbol, which I'm not drawing great on my screen, I'm sorry for that, is the symbol for an integral. Just like when we saw dy dx, it was really the delta y over delta x, but we use the fancy symbol because we're talking about it in much more detail. We're trying to get the change to be as minuscule as possible. Same thing here. The s comes from a fancy sigma, and we know that sigmas stand for sum. So that's really what we're talking about here. That's why we're talking about the area under the curve. We're summing up all of the area. So now back to our regular scheduled program. Let's say 6x plus 5 equals y. I'm going to do this the long way. I'm actually going to pull that one to the side for a second. And we're going to talk about the original rule. If we look at this, this means that I have a x to the b plus z x to the d. I'm going to change some variables around here. I know that before I did all of this, I had a x to the n plus b, let me change that variable. I don't want to repeat them. Nope. We're going to ignore all that. Back up, back up, back up, back up. I'm going to try this again. Okay. So our original function was ax to the n plus bx to the m plus cx to the z. When we got done, we had 6x plus 5 plus 0. We know that we were subtracting 1 each time, and we know that we were multiplying. Well, think about if we're going backwards. The opposite of multiplication is, dun dun dun, division. The opposite of subtraction is addition. So instead of subtracting 1, we're going to add 1. So that would give me 6x to the 2. But I know that I originally brought that 2 down, so to get rid of it, I'm going to divide by it. So same thing here. I had that 5, well, 0 plus nothing is 1, so 1, sorry, yeah. And then I'm going to go ahead and divide by that 1. We have an issue here. There's no way to really fill in the 0. We're going to talk about that in a little bit more detail, but let's go ahead and finish this really quickly. So that gives me 3x squared plus 5x plus, now we have this blank spot. This blank spot is where when you're in calculus, you're going to see plus c. So if you do not have what are known as bounds on your integral, you must add this plus c to your function. So we would say this. We don't have enough information to actually go back fully. We don't know what this plus c is. You would have to have more information to figure out what that is. You're going to learn that in your calculus class. We know, because we started with it, that it was actually a -10. But that's only because we were originally given it. If we didn't have that information, we would just say plus c, and this would be your answer. What do we mean by bounds? I could have said from 0 to 3. These represent x values. So that would have said then, okay, from 0 to 3, we did this integral right here, 3x squared plus 5. Sorry for my x there. Because we have these, this last term doesn't matter. The bounds actually allow us to evaluate it. You're going to bring it in. Once again, we're kind of talking about the opposite of derivative. This stands for delta, so we are going to do some change in here. You're first going to evaluate it with the 3. And then you're going to subtract it, evaluating it with the 0. Well, we got lucky here because this entire term cancels out. Zeros were easy. So this would just be 27 plus 15, which equals 42. Mental math, not always my forte. Let's say it's 42. So that would represent the area under the curve from x equals 0 to x equals 3. That's what we just did there. I just told you a lot. Let's go back to the original. How to undo the power rule. Just coming up with new variables here. So what we did, the first thing we did was we actually added 1 because we had to get that one back. And then we divided, but when we divided, we actually divided by that original 1 because this h plus 1 represented what the exponent was before we took the derivative. And we know that whatever that was before, we multiplied by it. So we had to get rid of it. You're going to do that same thing for every single term. So this one is going to be b to the x is k plus 1 over k plus 1. This one is going to be c x to the j plus 1 over j plus 1. So notice that we're actually dividing the whole thing. And then don't, forget that, I can't scroll apparently. If there are no bounds, you're putting plus c. So if you're just writing an equation, I know I shouldn't have used c twice there, but sorry. This plus c just says there's some sort of constant there. There's some other number that we don't know. So this is the opposite power rule. Just to make sure you know what you are doing, let me come up with some equations here. Let's start with derivatives. Go ahead and do those really quickly if you aren't actually doing that yet. Once again, I think those ones are pretty easy. You're just following that quick power rule of bringing the exponent down and multiplying it to the original coefficient and then subtracting 1 as you go. Let's see if you can go backwards. Let's see if we can take some easy integrals. Throwing a slight challenge one in here. I'm going to change that a little bit, just a little bit. Let's just make that a -3 on, and that reduces. Let's make it a -5 on top. So make sure that you did just catch on to that very last step I did there, which is reducing anything. We are in a much, much higher level mathematics course here. We always, always, always want to make sure that we are reducing everything. So this one, you should have put in your thinking cap. This is really -5/12 times x to the -2. We can deal with that. So that's using your exponent rules to recognize that if the x was in the denominator, it actually just means it has a -1. So if we follow the same rule, we're going to have our -5/12, and then we're going to do x, well, -2 plus 1. -2 plus 1 equals -1. So we're going to divide everything by -1. That means we're going to have 5/12 to the x times -1. We would still put a plus c here because we don't know. That's sloppy. And we can also go back and double check. We can say, okay, well, what happens here? Well, that becomes negative. And then -1 is x to the -2. And then that term would disappear. So we know that we did that correctly. So in case you aren't sure, you can always take the derivative of your integral to make sure that you did it correctly. So that's the end. Like I said, we will definitely do more of this as we go on, but I wanted to make sure that every student had kind of a starting point of what you need to know for calculus. And I will actually go ahead and post this document alongside it in case you didn't take notes, and also post this video, obviously, if you are watching this.